The figure above shows that the shaded triangular region with a hypotenuse of 5 centimeters has been removed from a rectangular tile with dimensions x centimeters by y centimeters. Of the following, which best approximates the area in square centimeters of the tile before the piece was removed? We're after the values of x and y, and we see that all three of these triangles are 30, 60, 90s, and so we can exploit the known ratios of 30, 60, 90 triangles to quickly move around this figure rather than taking up a lot of time using the Pythagorean theorem. For the center triangle, we know that the hypotenuse must be twice the short leg, so that makes the hypotenuse 10, and then similarly for the lower triangle, the short leg must be 5, which makes x 5 root 3. Now shifting back to the middle triangle, we have that the long leg of that triangle is also 5 root 3, which makes the short leg of the upper triangle 5 root 3 over 2. To get to y, we have to multiply 5 root 3 over 2 times root 3, which comes out to 15 over 2. And now that we have the values of x and y, we just multiply them together to get the area of the rectangle, and that comes out to a number very close to 65. Thomas is making a sign in the shape of a regular hexagon with 4-inch sides, which he will cut out from a rectangular sheet of metal as shown in the figure above. What is the sum of the areas of the 4 triangles that will be removed from the rectangle? Now at first blush, it doesn't seem like we have enough information to solve this, but the trickiest part of these geometry problems is sometimes that we need to draw additional lines. And so if we split this hexagon into 6 equilateral triangles, we start to see how to unlock this. This angle must be 60 degrees, and these sides are 4. And then onto this next triangle, we also have a 60-degree angle with sides of 4. And that leaves this angle in orange as 60 degrees as well, because the sum of the 3 angles must be 180. And so our old friend, the 30, 60, 90 triangle, emerges in the top left. The hypotenuse is 4, which makes the short leg 2 and the long leg 2 root 3. So our area is 2 times 2 root 3 over 2. There are 4 of them, so the total area is 8 root 3. An isosceles right triangle has a perimeter of 94 plus 94 root 2 inches. What is the length in inches of one leg of this triangle? My first guess was that the legs of this 45-45 triangle are 94 and the hypotenuse is 94 root 2, but that doesn't actually add up. So my next guess was that the hypotenuse is 94 and that the legs are 94 over root 2. We can rationalize that to get it into a recognizable form. That's 47 root 2, and that does indeed work. Now, if this method is too far out for you, we can also use the more conventional way of labeling the legs as x and the hypotenuse as x root 2. And so the perimeter is 2x plus x root 2. That must be equal to 94 plus 94 root 2. And if we solve for x, we get about 66.5. And the only reasonable answer choice then is B. In the figure shown, point O is the center of the circle. One vertex of the square lies on the circle, and the opposite vertex is point O. If the area of the shaded region is 36 pi minus 18, what is the perimeter of the square? This is actually a quick problem if you recognize your special triangles. The area of the circle is 36 pi, which makes the radius 6. And so the legs of this 45-45 triangle must be 6 over root 2. That times 4 is 12 root 2. In the xy plane, a circle has center C with coordinates hk. Points A and B lie on the circle. Point A has coordinates h plus 1, comma k plus root 102, and angle ACB is a right angle. What is the length of AB? We know that point A is 1 to the right and root 102 up from C, and so the radius of the circle must be root 103 by the Pythagorean theorem. We'll put our point B out here so that BC is perpendicular to AC. And now the key insight is that we have this isosceles right triangle, which must be a 45-45-90, and so the hypotenuse is root 2 times the length of the legs, so that's root 206. Now, we could have arrived at that answer using the Pythagorean theorem all the way, but it is quicker to keep everything in terms of radicals so that we can recognize the correct answer when we see it. In the figure shown, BC is parallel to AD and AB is equal to CD. What is the perimeter of quadrilateral ABCD? It's not obvious how to find the lengths of AB and CD using the picture as it's given. So let's draw some triangles for ourselves to make it easier. We can drop altitudes down from angles B and C to create these right triangles on either end. the altitudes must be 6 and the base side lengths must be 8 by symmetry. And if you recognize your 3, 4, 5 triangle scaled up, we have that side lengths AB and CD must be 10. And so our perimeter is 3 times 10 plus 26, which is 56. Could you have solved this problem without recognizing the 3, 4, 5 triangle? Absolutely. But I still maintain that you'll be far more likely to solve these types of problems quickly if you're primed to be on the lookout for special triangles from the outset. A square is inscribed in a circle with radius 6√2 inches. What is the perimeter of the square in inches? As always, if you can draw a picture, then you should. And once we have that up, we see that the diameter of the circle must be 12√2. And we have this lovely 45, 45, 90 triangle in the upper section of the circle. Its leg length must be 12, which makes the perimeter of the square 48. In the figure above, AB is equal to AD, BC is equal to CD, BD is 2, BC is 4, and AC is 10. What is the area of triangle ABD? We have a right triangle in which the hypotenuse is twice the short leg, so that makes it a 30, 60, 90 triangle. And so segment EC must be 2√3, and that makes line segment AE 10 minus 2√3. So the area of triangle ABD must be 10 minus 2√3 times 4, the length of BD, divided by 2, and that is C. A rectangle is inscribed in a circle such that each vertex of the rectangle lies on the circumference of the circle. The diagonal of the rectangle is twice the length of the shortest side of the rectangle. The area of the rectangle is 1089√3 square units. What is the length in units of the diameter of the circle? Again, we have a triangle such that the short leg is half the length of the hypotenuse, which makes this triangle a 30, 60, 90 triangle. And so if the short leg is x, the long leg must be x√3. And so the area of this rectangle is x squared root 3. And that gives us an x value of 33, so the diameter is 66. In the xy plane above, O is the center of the circle, and the measure of angle AOB is pi over a radians. What is the value of A? We have that point A is at root 3 comma 1, and anytime you see root 3 on the SAT, that is a big fat clue that a 30, 60, 90 triangle is lurking. And sure enough, there it is. We have that the long leg is root 3 times the short leg, and so angle AOB is 30 degrees. Now, if we multiply 30 degrees by the conversion factor, pi radians over 180 degrees, we get pi over 6 radians, and so A is 6. If the sound of the word radian gives you a cold shiver down your spine, then check out my previous video on arcs of circles, and that should resolve that shiver in a little under 2 minutes. The figure above shows a regular hexagon with sides of length A and a square with sides of length A. If the area of the hexagon is 384√3 square inches, what is the area in square inches of the square? Now, most students are going to read this problem and freak out and think, I don't remember the equation for the area of a hexagon, and the equation is not in the cheat sheet. What do I do? Stop freaking out. Draw triangles. You can split the hexagon into 6 equilateral triangles and then split one of the equilateral triangles into two 30, 60, 90s. The short leg is a over 2 and the long leg must be a root 3 over 2. That means that the area of one of these full equilateral triangles is a squared root 3 over 4, and there are 6 of them in the hexagon, so we have that area must be equal to 384 root 3. That leaves us with an a squared of 256, and that is the area of the square. To see more like this, subscribe to the channel and check out my next video on similar triangles.